All right, so good morning or afternoon or evening whenever you're watching this. Today we're going to be talking about vibration and impact loading. And vibration is something that's present in pretty much all machines are subject to vibration. Every structure has its own stiffness and mass, and anything with this stiffness and mass, even a little block of aluminum, will have its own natural frequency. And then we're also going to talk about impact loading and a way of doing a simple energy analysis to get a first order estimate of the loads that we expect during impact. And we'll talk about some examples. I'm also going to show you some examples from our research where we get the natural frequencies of a real structure. So just a little bit of review. You've probably all seen the mass spring damper that can represent a system such as this actual system where we have a cam and roller, and here we have, this would be the mass, this would be the spring. The friction would add damping, and any internal energy losses in the spring would also add some damping. The lumped parameter modeling that we do for these types of system is sufficient to get the natural frequency of that specific mode shape, but in reality this is a continuous structure which has all sorts of vibration modes, not just along the axis, but you can have vibration modes, a lot of different vibration modes that are throughout this structure. Some modes have more than others, and usually the fundamental frequency, or the first natural frequency, is the one with the highest mode. If we're talking about a lumped parameter system, we can analyze this by summing forces, as we did in dynamics. We say that the sum of the forces on this is the right-hand side is equal to our mass times our acceleration. If we put all the terms with x's on the left-hand side, that allows us to do the Laplace transform. If we define the force due to the spring as F over y, the force for the damper as the force over the velocity, that's what we're doing in this simplified model here. The natural response of the system is if the force is 0. So if the force is 0, we can divide both sides by the mass, and then we get these terms here, the d over m term and the k over m term. And we know from transient analysis that this d over m term is actually twice the damping ratio times the natural frequency, and that this k over m term is the natural frequency squared, meaning that our natural frequency is the square root of k over m. So the stiffer something is, the higher the natural frequency. The larger the mass with the same stiffness, the lower the natural frequency. We think in terms of frequency, often in terms of hertz, but when we do the analysis, this is in angular frequency, which is in radians per second. So if we wanted to convert those, we can divide by 2 pi radians to get things in terms of hertz. And the damped natural frequency is usually what we see from the response. Okay, so when we see the oscillations from a system that has been excited, what we're looking at in the transient response is the damped natural frequency, and the damped natural frequency is less than the natural frequency, depending on the damping ratios, how far they are. The damping of the system is how far away it is from the natural frequency. So this is kind of what we have learned so far, to think in terms of a system, and it can help us to get a rough order of estimate of the frequency of a system by doing this type of analysis. But in reality, when we have a system, that structure can actually be excited in various mode shapes for a continuous structure. So let's say this is an example of a musical instrument. We can have this shape here. If we pluck it, we can get this shape. But we can also excite the string and get this shape here. This is our second mode, third, fourth, fifth, sixth, seventh mode. Then as you can see, the amplitude goes down as we get into the higher mode shapes. Okay, and if you see this here, when we go to the first to the second mode, we have half when we go from the second to the third, we get a third, and we get a fourth, fifth, sixth, and seventh. And what's interesting to note, something you should be aware of, is when you're trying to measure the vibrations in the structure, if you have one of these higher order mode shapes and you were to place a sensor right here, right here, right here, right here, let's say an accelerometer, you're not going to get much of a signal because that's a node in that mode, and or an antinode, and that's where you really have zero output if you have this oscillation going on in your machine. So if you're measuring vibrations, where you place the sensor can really matter. And so sometimes you just need to move it around and try to find where you feel the most vibration. And obviously, if you wanted to get the greatest sensitivity, you'd put it at the peak of a mode shape. So by analogy, this is kind of where we have lived for the natural frequency, but continuous structures can have a higher order mode shapes as well, as seen just here in the example for musical instrument. Okay, so one of the sort of best ways to highlight that is for us to just take a look at a video that shows a two-dimensional continuous structure that's excited with base excitation. I'm trying to click on here, follow this link. Okay. It doesn't want to go to the link for me, so let's see if I can do it this way. Okay, that seemed to work. All right. So if we...
It's not that easy, but Grammarly can help. This sentence is...
So here we have a shaker, which gives input to the system. We have this continuous system here, and then we have this function generator which drives the shaker, and then just some regular old salt. So they place the salt on the plate and then generate different frequencies, and depending on the frequency you can see how the structure is going to be excited, and where you get these mode shapes, and you get these nodes where you have smaller amplitude vibration. Okay, so that was a lower frequency. As we increase the frequency here, this is going to 1033. You can see we get higher modes. Okay, this is 1820. And you can get various different shapes of the structure depending on how you excite it. So for us to think in terms of the natural frequencies is useful, but the reason I'm showing you this video is you should also be aware that in a real continuous structure, depending on the frequency of input, you can get all types of mode shapes and excitation shapes. So if we go here, I mean, we can get some pretty cool shapes. This is all the way up at 5,201 hertz, and it's just pretty fascinating. Okay, so it's important for the machine designer to also think in terms of frequency. And this is a pretty cool quote from Tesla. It says, "You want to find the secrets of the universe, you got to think in terms of energy, frequency, and vibration." So for our purposes, we don't necessarily have to consider all of these things initially, but if we have a machine that will be subject to vibration loading, then it would be important to do the structural analysis and look at the various mode shapes and the excitation mode shapes, because it can have a very important role in fatigue, particularly failure. This is an example here from our research of how we can do some modal analysis by taking an impact hammer where we whack a structure and then have a sensor. In this case, this is a accelerometer that is integrated twice so that we can get the displacement. And then we can actually get the modal analysis, or the frequency response function, between the input and the output to look at the frequency response of the system. Now, for this case, we're interested in getting stability lobes. This is particularly of use for machining dynamics to predict chatter, and that's what this project was about. The frequency response function compares the input to the output transfer function for that structure. If we measure the displacement, we call the frequency response function between the force and the displacement the receptance of the machine, or the compliance. If we look at it between force and velocity, we call it the mobility. And if we look at it between force and acceleration, we call it the accelerance or inertiance of that structural system. And that's really just the frequency response between the input and the output. And when you do that frequency response, you can get a real part as a function of frequency, and you can get an imaginary part as a function of frequency, and you can actually relate each one of these modes to a natural frequency and damping. The way we do that is we just take an input force sensor from an impact hammer, and we take an accelerometer. We measure those signals with an analog to digital converter, double integrate the acceleration to get displacement, take the Fourier transform, and then do the FRF analysis to get the output over input relationship. This is the hardware that we use. This is some National Instruments hardware. This is the impact hammer. This is the data acquisition card. This is the measurement hardware from National Instruments. This is the accelerometer. These are the part numbers and units and sampling rates. And this is a 5-axis machine. And so in this case, what we try to do is put a tool in the machine, put an accelerometer on the tool, and then we whack this side with the hammer, and then we look at the response. So this is the hammer input here. This is the acceleration output, so we can take the frequency response of both of those to get the FRF. We can decompose the signals with the area of interest, and we get something like this in the real and imaginary. And as we saw, each one of these peaks can be related to a frequency that's present in the system, a natural frequency of the system. And you see, so for continuous structures, we actually have an awful lot of frequencies, and you see here at this frequency, we have a lot more energy. Okay, and that means that the response is much higher to that input force, which means this frequency is a lot more sensitive to being excited, and something that we should pay attention to. So we can take that data, we can process it into our real, imaginary, and magnitude and phase plots to look at it in different ways. And you can see we have that peak there, close to 6 kilohertz. That's that will be of interest, but also these earlier frequencies here may be actually easier for us to excite because they're a little bit lower. And so if we are, if we have a rotating machine or a motor, and we're going to be passing through these frequencies as we get up to speed, then we just have to be careful we don't stay at any one of these frequencies too long. Okay. So the amplitude plots and phase plots can be used then to the real and imaginary parts of those plots can be used to then pick out these peaks and valleys for each one of these response shapes for the frequency content. And by picking these, we can actually extract that frequency where that energy shows up, the effective damping at that frequency, and the modal stiffness, which is sort of a stiffness of that system at that frequency. Now, we got all of this, all of these responses. We had all these frequencies, and they were all present in this system here. So the dynamics of the tool and holder and spindle and machine dynamics can all come into play when we're looking at this. Even though some of these are a lot stiffer than others, you can see that even in this large continuous system, that we have a lot of different frequencies that show up. Okay. Now for our research, we'll use this to predict chatter and then try to stay away from frequencies that we know will have higher energy than others. Okay. So we'll give an example of some basic frequency analysis a little bit later, but now we're going to talk about impact loading. So impact loading is a loading event that has a short duration, okay, as opposed to static loading where we'll load it up and then that load stays there forever. If the time of the loading from zero load to peak load is less than half the period of the natural frequency of the loaded structure, then it's considered impact loading. So, do we know if we experience an impact? Well, what we would need to do is maybe have some information about that structure, maybe do a tap test, and find out what its natural frequency is, or take a look at the first mode for the structure that you're looking at to see what the frequencies are of that structural system, and then you can compare that to how long the contact load is. So this may require some testing or some simulation or whatever for you to kind of get that information. If the time of the loading is greater than 3 times the period of the natural frequency, okay, then it's considered static loading, and in between is a gray area. So the period of the natural frequency is just 1 over the natural frequency, or in terms of angular frequency, it's omega n over 2 pi. Okay. So this is a summary. If the time to the peak load is less than half the period of the natural frequency, and we consider it impact. If it's greater than 3 times this natural frequency, then it's considered static. Okay. And all right. So there's different classifications of impact loading. So striking impact is when we actually have a collision of two bodies, such as hammering. Force impact is different. It's when you have a sudden applied load without the velocity of collision. So you can think of it as like a weight being taken up by support, or the application of a clutch or brake, or disengage and engaging. Both striking impact and force impact can actually happen simultaneously, but that's how we classify them. Okay, so striking impact will involve velocity. Force impact doesn't involve the kinetic energy associated with velocity. It has more to do with going from a zero load to a non-zero load in a relatively short amount of time. Okay, so there's the dynamics of impact loading can be pretty complicated to analyze, but we can get a sort of the back of the envelope order of magnitude approximation by using the energy method. Okay, and we can use this if the mass of the striking object is much larger than the mass of the struck object, sort of in the case of a hammer hitting a nail. Then we can consider that the striking object is big and rigid, and that the kinetic energy of that striking object will be related to the elastic energy stored in the struck object at its maximum deflection. The energy method gives us an approximate value for impact loading, but if we wanted to have more precise analysis, we'd actually have to look at the the waves of stress and analyze how they go through that material, but obviously it's beyond the scope of this course. You could take the theory of elasticity and some advanced finite element analysis classes and start to look at the mechanics of these events in grad school or self-study later on. But for us, we can just look at the energy associated with impact. If we represent the energy E here as 1/2 kx squared, or in this case k delta squared, that's the energy stored in a spring. The force of a spring is just the stiffness times the displacement. In this case, we call the stiffness K, and the displacement delta. Okay, the stiffness is the force over the displacement. So this is a lot of these parameters we can measure. The energy then we can express in terms of force, and it's just 1/2 times the force times the displacement. So if you looked at a force displacement curve, you could just take half of that area that's traversed, which would be the triangle of that force displacement, and that's the energy, the elastic energy that's stored in that spring or in that structure, which is really a spring that deflects delta. Okay, and it's important to think in terms of structures as, they're also springs with stiffness. We have the stress strain diagram. We have Young's modulus, which tells us the relationship between stress and strain, and it's a measure of stiffness of a system. We can also rewrite and express the energy in terms of the applied force squared over twice the stiffness just by playing around with these equations. Okay. Now, here is an example of horizontal impact. Okay, and in this case, what's important is we're actually looking at the velocity. We have to modify the energy that's transferred during impact by eta, and that's related to the energy dissipation of that material, and this is something that we can look up. There's a author that has worked on that. We'll show one of his charts in the next page. If the energy dissipation for that material is relatively small, then we can just assume that eta is 1. And in this case, we can say, well, the energy, according to that material, the energy dissipation of the material of that slide is 1/2 mvi squared. And we can assume that all that energy is then transferred into the deflection of this structural object. And if so, we can get an expression for the force of impact, which is related to the velocity times the square root of eta times the mass times k. The static deflection, from the mass with the weight would be just the weight over the force over the stiffness, the weight, the mass times the gravity over the stiffness. That would be our static deflection. And if we want to know the ratio of the deflection from impact to the static deflection, which would be this impact from the force over the static impact, we can actually get a term like this, where we look at the impact force over the weight, which allows us to look at the deflection due to impact over the deflection due to the static loading case, and it gives us this term here. And this term here is what we call the impact factor, and it gives us a ratio of the force you experience during impact versus the force you would get if you just set that object on that weight. So this term is the impact factor. The static deflection is something we can calculate. So we can calculate using our understanding of the deflection of the structure, or we can measure it from a force equal to the weight of the mass that's going to strike the object, and then we can estimate the dynamic force using this information. Now, this is for horizontal impact, and this also works for any other axial loaded members, even if they're in bending and torsion as well. So this is the energy method of looking at the kinetic energy and how that energy is transferred into the elastic energy. and then giving us some terms that we can use to estimate the impact due to that weight hitting, which is a function of the velocity. Now, if we have a vertical impact due to, say, a mass falling some distance h, then we can still use the potential energy of the falling object. In this case, we have this kinetic energy, and that kinetic energy is actually equal to the potential energy for that falling object, which we can represent here. So the key thing is we've introduced this eta, though, that's dependent on that property, and we can look at that energy. Now, this equation is sufficient for small if the deflection is small compared to the height that it's dropped. If it's not, then we have to also include that energy stored during impact. So we can do that by looking at the energy of the system, which is the potential energy, plus the weight of that object times the impact displacement due to that weight. In this case, we then can go back to the relationship between the force of impact that we saw 2 slides ago, and then relate that to the collection of terms for the potential and stored energy in that system. So if we go through that analysis and we collect terms and substitute the force back in, then we can get the force to show up as a quadratic term over the weight, and we can get it to show up here as the second term, and then we have a quadratic equation. So then we can solve this quadratic equation and get the roots to find Fi over W. So we get the root Fi over W, and then this is related to the impact factor here, in this case for vertical impact, where we have it falling. And we have this right-hand side term as well, which is the impact factor. Now, this can be used for falling weights. And notice what happens if the height is 0, then the force due to impact is actually twice the weight. In reality, it's higher than that. It's usually 4 or 5 times. That's what 3 to 5 times. That's what people will commonly use to give a safety margin. But as you can see, just going through this analysis, even if the height is relatively 0, but you do have an impact event, it's going to say that the force due to impact is twice the weight. Okay. In this case, to find eta, Burr has done a lot of analysis. This is his correction factor for a mass that's axially impacting a rod. This is the case we have here. And in this case, we can look at eta, and we can get a number. And then M here is the mass of the striking object. MB here is the mass of the struck object. And that gives us a ratio here. Now see, eta is approaches 1 when you have much higher mass ratios, where the mass of the striking object is a lot bigger than the mass of the struck object. In fact, if it's 20 times bigger, then you can consider eta to be almost 1. If they're smaller, you get smaller numbers for those mass ratios, because that elastic energy then it's going to be shared more equally between those 2 objects, and you can correct for that using this approach. And we'll walk through an example. Okay, so this is a way for us to have some tools to look at the forces that we might expect if the structure that we're designing or machine or whatever experiences an impact event. In that equation for the vertical drop, as we saw, if the impact force is a sudden load, okay, we would call that a sudden load without velocity, then the force due to the impact is actually twice the weight. Okay, and this goes back to what we were talking about between the striking impact and force impact, and that would be the sudden load that's applied without velocity or collision. And so using this analysis, if we don't have this collision, okay, where we have H as 0, where we just kind of place it on, but we didn't drop it, but we go from non-zero load to zero load, then we still are getting some forces that are initially going to be twice as high as just considering the static weight of that object. Okay. Designers usually use factors of greater than 3 for sudden loads. So it's something that you have to be aware of when you have loading in an object. You have to design against the impact loads and sudden loads that you'll see in your system, and make sure that you're sufficiently far away from any of your failure stresses. Okay, so we're going to pause here and then do some examples.